The Arc Fault Detection Device, or AFDD, was first mooted for the UK market way back when 18th edition was but a naughty twinkle in the eye of the IET as they went out for drinks with BSI, and as sometimes happens months after a drunken date, at the beginning of July this year 18th edition was born, plopping out onto the carpet, kicking and screaming. So, AFDDs have made it into the book. I've been trying to get hold of one of these devices via the wholesaler route for some time, but without much success, even if I'm armed with a part code, and there doesn't seem to be a great deal of information out there about what these things are and how they work, even though they're popular in America, Australia and several of our European neighbours. But this is the Crabtree model, and I must thank my friends at Electrium, part of the Siemens Group and purveyors of such venerable brands as Volex, Wilex, Appleby and of course Crabtree, because Electrium have generously provided me with their current AFDD offering so that I can make this video today. So not only am I lucky enough to have my hands on one, but I'm also lucky in the fact that this is not just any old AFDD. Oh no folks, this is a market leading model. What I have here is a 3-in-1 device with overcurrent, earth fault leakage and arc fault protection, and yet it has a smaller footprint than the Eaton equivalent, which is a third larger and takes up 3 fuseways instead of 2, while the Schneider offering, from what I've seen, is the same size as this but lacks the earth leakage element altogether. So we and Worthy should kneel before this Crabtree wonder, as it is a very capable bit of kit indeed. Looking closer at it, you may spot we have 2 devices mated together here. On the left is the arc fault detector itself, branded as Siemens in this case, but I'm told that if a Crabtree or Wilex part code is ordered, then the Siemens name will be excised for the UK market. Now on the right is a standard miniature RCBO, and if we compare it to another miniature RCBO from the Crabtree range, you can see that the 2 devices are joined together by a connection piece at the top and by a couple of metal clips on the front. And indeed, if we find a little screwdriver here, we can pop off these front clips. I've already undone the screws in here, and yes indeed the RCBO element detaches from the AFDD part. So that's jolly clever and allows sort of an upgradable retrofit kind of device. I'm trying to get back together again there. Hope I haven't broken it. And so these clip back on, and I'll do the screws up later. I believe that if you order in an AFDD, you choose the size of the RCBO that you want to accompany it, and that they are supplied together as a pre-mated unit from the factory, but we'll see about that. Now, have it on good authority too that all of this package will be shrunk down into a single miniature RCBO form factor very soon, and that such a device is already on the German market. So the expectation is that by the time the wiring reg shifts its wording for AFDDs from recommended to required, well, then the market should hopefully by that time be sporting 3-in-1 devices that fit into one existing fuseway. So hopefully we don't have to throw our hands into the air in exasperation at the size of the consumer units of the future. I need to mention one other design feature of this Crabtree product, which is that it's part of the Starbreaker family. If you're not familiar with Starbreaker, well, it's a clever board design with a unique buzzbar arrangement. If you look on the underside of these Crabtree devices, whether it's the AFDD RCBO combo or an RCBO or an MCB, you'll notice that there is no buzzbar cage clamp like you would expect to see, and unlike you would see on the sister range from Wilex here, where they have the usual arrangement. Instead, the Starbreaker has this safety buzzbar feature, which means that if you're performing some live diagnostic work, then the shock risk is much reduced. The protective devices have a tab on the rear, which allows them to simply plug into place. This, of course, reduces installation time, and it reduces the risk of a loose connection or a misaligned connection at the buzzbar itself. The advantage of the Starbreaker range for the AFDD product is that it's an easy retrofit for existing boards. It just plugs in. Unlike the Schneider and Eaton rivals, which would require removal of the existing buzzbar and some chopping and changing of it for their AFDD products to retrofit into place. Now, this particular Amendment 3 enclosure has a single buzzbar, so it's ideal for RCBO or AFDD retrofits. But I have here on my pile this pre-Amendment 3 enclosure, also from the Starbreaker family, and kindly donated by Arthur and Ken at my local branch of CEF, old Kenny being one to never throw things away, just like me. This larger enclosure has a split buzz bar arrangement, so we have here a main switch and high integrity fuseway on the left, then two separated buzz bars for split load use, like in a dual RCD arrangement. The point is, a new device such as the AFDD can retrofit into these existing older boards quite easily. And worst case is that you may need to order in a different buzz bar configuration. So if you wanted to lose the split load and go fully RCBO or RCBO AFDD combo, but you could still keep the same enclosure on the wall. Before I demonstrate the arc fault detection device I have here, let's have a quick rundown on just what this thing is. The arc fault detection device, or AFDD, is also known as an arc fault circuit interrupter, or AFCI, elsewhere in the world, because as a species it seems we can't standardise on simple nomenclature for some reason. This is a device which interrupts the power upon detection of an electrical arc signature. Any electricians watching will, I'm sure, have seen an arc, but for those who haven't, this is a slow motion recording from a 10 kilovolt arc generator I built over 10 years ago and featured in a previous video about insulation resistance. An electrical arc is formed when there is a potential difference big enough to jump the insulating layer between two separated conductive parts. In most cases that'll be a simple loose connection where the copper wire isn't in proper contact with the terminal and there is a small air gap between them. As I explained in that previous video, air is an insulator, but the resistance of its insulation changes with temperature, humidity, airborne particles and other factors. Any insulator can be electrically overcome if you have a big enough electromotive force, so the larger the air gap between your conductive parts, the higher the voltage needed to break down the insulation of the air between those conductive parts to jump the gap. In the case of the UK domestic main supply at around 230 volt, a millimetric air gap will likely result in a broken connection that can't be jumped, but if conditions are favourable, then an arc can form across the gap. Impressive though my 10 kilovolt arc generator is, I'm going to show you a much smaller and more everyday arcing event with the aid of my custom built 230 volt high precision arc fault simulation apparatus. And here it is, the patent pending DASWACAN 1000, or the Dangerous Arc Simulator, with a clumsy acronym name to give it its official title. Now, believe it or not, I actually made this impressive piece of laboratory hardware myself. Yes, those clever Germans, they may be able to squeeze an arc fault device, RCD and a circuit breaker into a single miniature RCBO form factor, so I'm told, but we British still have homegrown engineering talent, proof, if it were needed, that we will survive the Brexit shambles. And look, I thought these stars and flowers were rather spiffing additions. But enough of the aesthetics. This apparatus allows me to simulate a loose connection at 230 volts through the manipulation of this precision adjustment wheel, which, as you can see, moves the control wire on the left side away and toward the fixed wire on the right hand side. The load on the end of this wire is a 1500 watt heater, which is pretty nuts considering it's over 33 Celsius here in the office today and I can't turn on the fan while I'm recording. But 1500 watts is a good high load, about 6.5 amps of current, as we'll soon see displayed on the attached clamp meter. Okay, so when I operate the DASWACAN 1000, the induced loose connection will cause the heater to rapidly switch on and off, and so we'll see some arcing action where the wires are joining and separating. So without further ado, let's plug in and power up. There we go. Okay, that's on, the heater's on, clamp meter on. Let's just make sure you can see the display on that, and we're drawing nothing at all because we have a tiny little gap between the wires here. Okay, so let's join them together. It says, there we go, about 6.5 amps, 6.3 amps, which is what we expect at 1500 watts. Okay, now we've already just seen a bit of arcing action there. The heater is on, you'll have to take my sweaty word for that, but we know that the clamp meter is recording the current there. So I'm going to move the adjustment wheel here, and I don't know how well the microphone will pick it up, but there are visible and audible arcing events going on as my two wires slide up and down each other here. I don't quite have the granularity of control, I don't think, to maintain an arc. It's just a very brief zap event, and then it's either connected or it's not, and it's all over. I was hoping to get a bit of a buzz going on there, but it's It's not happening. Maybe the DAS-WACN 2000, if I ever make it, will have finer adjustment, but I'm limited to the bricks and cogs available in my kids' Lego set here today, so we'll just have to prat about a bit with what we've got. I think we'll have a closer look at that. Okay, I've adjusted the camera for a closer view, and I've also turned off the office lights so that hopefully we can see visually the arcing event a little better, a little clearer. I've just checked the previous clip as well, and I can see that the microphone is picking up the noise of the thing. So as I use my adjustment wheel on my precision apparatus here, we can rub these wires together and generate some miniature arcs here. Oh, fairly big one there. Obviously you shouldn't look at an arc with the naked eye, you should have eye protection, and of course I've got all the correct PPE behind the camera here, as far as you lot know anyway. I don't know if it's picking it up. There's always also the odd bit of smoke and sooty deposits as well, and these wires, if I were to zoom in more, you can see have been fairly blackened by today's playing around. Now what we're witnessing here is series arcing, that is an arc between 2 points on the same line. This kind of fault wouldn't ordinarily cause a problem for the protective devices we already know and love, as the kind of current being pulled here is much less than the rated breaker value, so there's no overcurrent event. It's also not a fault to earth, so it won't be troubling the RCD with this kind of in-circuit malfunction. Nevertheless, this fault has its own dangers, as it can cause a fire. At the point of arcing, we have a high resistance, high temperature joint, and as the temperature increases further, so does the resistance, and we end up with this vicious cycle of resistance causing heat, causing resistance, causing heat, and so on, with things getting worse over time. Eventually, the local insulation surrounding plastic parts will be damaged by overheating. If we're lucky, the joint will simply fail and the damage will be incurred when an electrician is called out to identify why the circuit is no longer functioning. If we're unlucky, surrounding material may ignite and start a fire. Electric shower isolators are particularly prone to this problem, as they use relatively thick 6 to 10 mm cables which work loose in the isolator screw terminals and fizz away under a high current load until the isolator melts around the terminal. I change out several of these things every year because of this kind of fault. In theory then, the AFDD should detect the arcing event at my apparatus, and it should trip off to remove the power to my electric heater. So here I now have the AFDD wired in circuit, still with the electric heater connected, although there's no load currently going down the wire, as we have them separated at the DAS-WACN 1000. But by adjusting this, as I will now do, I can introduce some series arcing into the circuit, and we should see the AFDD hopefully recognise that fault and trip off. Now I'm going to cheat a bit. I'm going to add a little bit of salt water to my wires just to help prolong the arc and give it a bigger magnitude, bigger bit of fizzing away there. Because the short ones we saw earlier won't actually trip the device as they were, and for reasons I'll explain later. Incidentally, electricity, water and Lego are never a good idea as a kid, so don't try this at home. There we have it, a rather spectacular arc event there. The red light on the device is now extinguished, as you can see, and if I try to flip the switch back on, you can see it's all gone rather limp. By pressing the reset button on the AFDD, I can now restore power, and indeed, although we have a different indication light, power is now restored to the wire here. But we now have a flashing yellow light to indicate the trip event was down to a detected arc fault and not an overcurrent or earth leakage fault. I can press the reset button again and the alarm condition is cleared, giving us our normal red status light again. If called out to one of these things because it's tripped, then my job would be to find that loose connection, and my goodness, that might be a tall order, especially on a circuit with a lot of points, such as a socket outlet circuit. I'll start by looking at each connection point for trapped insulation or a loose connection, probably just loose by fractions of a millimetre, and probably with no telltale localised heat damage to act as my smoking gun, because the AFDD will have clicked off before any heat damage occurs. After all, that is the point of the thing. If I'm lucky, I'll identify the issue via dead testing with an ohmmeter and or by inspection at every point. If I'm unlucky, the fault will be in the supply wiring buried within the property, say a damaged cable or a moody hidden junction box that was improperly installed by a previous homeowner and which nobody else knows about and is now hidden under a laminate floor.
Tripping events with AFDDs, especially in retrofit applications on older installations, could be a bit of a headache. Even if you think you've tested and traced a circuit fully, there may be some odd hidden spur branching off somewhere that you just haven't spotted. So if I turn up to a tripped AFDD and I see a flashing yellow indicator, at least with this model of device, I know I'm looking for an arc fault as the cause of the trip. If it goes bang when I turn it on, I guess I'm looking for an overcurrent fault. So how do I know if I'm looking for an earth fault? Well, let's introduce an earth fault with my metrel tester here. I've removed the heater load from the circuit. I've connected together the wires of the DAS WACAN. You know, I'm going to stop saying that because it was a crap joke and I'm sounding like a moron. Anyway, my metrel tester is now connected, so I can inject a 30 milliamp fault current to earth, which will test the RCD element of this device. Let's reset the visual indicator here. So we've got our red status light back again, and we'll press the test button on the metrel. And what should happen is this should trip off within 300 milliseconds. That's it, as it's a device that's compliant with BS EN 61009. There we have it, 25.2 milliseconds. I'll just reset it. And notice the indicator light on the device shows red, so that tells me I'm not looking for an arc fault as the cause of that last trip. Remember, the AFDD here is a separate unit to the RCBO that accompanies it, and the AFDD isn't concerned with overcurrent or earth faults. It doesn't know anything about them. All it knows is that it's lost its power because the connected RCBO either tripped off or switched off. So we can see from the visual indicator if we're looking for an arc fault or if it's a traditional overload or earth fault that could trouble any RCBO. By the way, the reset button on the AFDD also acts as a test button and trips the RCBO if pushed. And of course the RCBO has its own trip test function. Now, while the RCBO test function is little more than a test of the mechanics, the AFDD test button, I imagine, instructs the electronics within the thing to trip the RCBO as though an arc fault has occurred. If the AFDD test button doesn't work, then there's potentially a problem with the electronic brain inside here. One other thing to mention, and something I missed in last week's video about changes introduced in 18th edition, the stock RCD test notice would also now apply to AFDDs, but in 18th edition the frequency of recommended testing has changed from quarterly to biannually, so you now have another device to be testing, but once every 6 months instead of every 3.
I've shown this AFDD operating with a series fault, but it can also detect a parallel arc, that is, an arc between line and neutral or a line conductor to earth. We're not talking about a direct short, as that would result in an overcurrent or earth leakage operation of the RCBO portion of the device. So again, this is arcing where the circuit remains in operation, at least for some time, as the nature of the fault is such that it doesn't breach the operational rating of a breaker or RCD. But nonetheless, there's a voltage jump across a compromised insulation layer. In the case of a parallel arc, it wouldn't be down to a poor connection like we saw with my apparatus earlier, more like a crushed, overbent or physically damaged cable, something where the insulation has been squeezed down, gnawed at or chafed off.
So this is all very well, but what about natural arcs? And by that I mean arcs formed on electric motors or the action of any mechanical switch, relay or contactor. I can demonstrate some natural arcing with this electric drill, which as you'll soon see spits out some arcs and sparks in its normal operation. I'm going to try and get this right up close to the camera here, and within here we should see, well, we're going to get horrible noise, but we should see some fizzing action going on. How well the camera picked that up, and I'm deaf in one ear now. But notice that the AFDD, which the drill is plugged into, has not been troubled by my drill shenanigans, as it recognises the arc signatures of this device being natural or friendly. That's also why I had to put salt water on my apparatus wires earlier, as the arcs formed by simply rubbing the wires together are not the kind of arc signature that this device is looking for. They're individually too short, although there are many of them, but they're essentially the same kind of arcs that we're seeing from our drill motor. The salt water here was needed on these contacts to provide a lower resistance medium than the air in order to prolong and intensify the arcing event to meet the troublesome signature the AFDD is looking for. The clever monitoring here keeps nuisance tripping at bay. As mentioned earlier, everyday friendly arcs can also be formed in mechanical switching, such as when you throw a light switch or the switch on the face of a socket outlet. You're bashing together two brass contacts within it, and if you view that at a microscopic level, you'd see that these two contacts don't just cleanly join together. Instead, they clatter together and bounce off each other. It's not a clean connection, but for most applications, it doesn't matter, as the bouncing is measured in thousandths of a millimetre and it's all over in microseconds. But as those contacts bounce off each other, the electrical connection is made and broken several times. And as those contacts pull apart from each other, small brief arcs are formed. You can sometimes see the effect of this if you pull apart old switches and sockets, where you'll find sooty deposits around the switch contacts. In fact, I can demonstrate the switch bounce effect with this quick breadboard knockup that I've made. What I have here is a 2-digit display controlled by a pair of 4026 integrated circuit counter chips. For every pulse received by the counters, the display will increment by a factor of 1. So the expectation of throwing this mechanical light switch once is that the display here will change from 00 to 01. Instead, when I flick the switch, the display in this case shows 7. That means the brass contacts inside this switch have bounced off each other, making and breaking their contacts 7 times on this single switch throw. Let's reset it and try it a few more times. And notice turning the switch off as well also incremented the counter there. So the act of the brass contacts pulling apart can also cause some bouncing effect, which would in itself produce arcing within the switch. I'm just going to reset that. And we'll do it a few more times, see if we can beat our low score there. Got 10 or 11 that time. 13. Unlucky for some. Oh, 24. That was a good one, wasn't it? 11 up to 13. 20. So you can see that the result is never just 1. Blimey, there was quite a few that didn't pull apart cleanly on that one at all, did it? It went from 9 to 16. So you can see that the result of me flicking the switch once is never that just one appears on the display there. And it's for this reason that an electronics designer, when working with a mechanical switch, may have to build in components to debounce the switch, i.e. to flatten out the spikes caused by these contacts clattering off one another. In this case, with this particular circuit, if I reset it, I can debounce this circuit by inserting a 100 nanofarad capacitor. I simply put that between ground and the output of the switch, or the input to the counter, whichever way you want to look at it. And now when I operate the switch, it does exactly what we want. It increments by 1 every time. So this capacitor is flattening out the spikes caused by the contact bounce, and as you can see, the thing is now working as it should do. Of course, the capacitor is not stopping the mechanical bounce, it's just ironing out the effects of it for the electronics.
At this point, I know what you're thinking. 3 things are going through your head right now. Firstly, you're wondering why you're watching this sober. Secondly, you're wondering why you still listen to me drone on when there are far more interesting videos on YouTube. And thirdly, you're wondering what would happen if I stuck that 10 kilovolt arc generator we saw earlier onto the output side of this thing. Well, let's do that, but the result may surprise you.
Okay, I now have my 10,000 volt arc generator, known as a Jacob's ladder, connected to the output side of my AFDD device. So when I turn the power on, what's going to happen is the AFDD going to allow this dangerous arc to buzz away there, or will it cut the power? What do you think? Think about it now. The answer is no trick.
So why does a 10 kilovolt arc not bother it? Well, it's simple. My 10 kilovolt arc is not on the distribution side of my electrical installation. The AFDD is looking for an arc signature on the distribution wiring. That's what it's connected to. But my Jacob's ladder doesn't induce any arc interference onto the supply. All the arcing action is only on the output side of my step-up transformer. Therefore, the AFDD just doesn't see it. And that's something to bear in mind with arc fault detectors. If an arc forms on the load side, i.e. within an appliance itself, and it is isolated from the distribution wiring by means of a transformer or other electronics, then your AFDD will not be troubled by it. This means electronic appliances with faults such as dry solder joints or internal loose connections could still be a fire risk without bothering any of your protective devices. But then fuses, breakers, AFDDs, and perhaps to a lesser extent RCDs installed at the source of the installation are really all there to protect against faults on the distribution wiring, not necessarily faults on consumer electronic equipment. When it comes to arc fault detection, it's applied per circuit, like overcurrent protection, but perhaps unlike RCD or surge protection, which are often applied to a group of circuits or to the installation as a whole. This means you wouldn't use one AFDD per installation, but rather one per circuit, and although 18th edition only recommends their use, it doesn't specify on what kind of circuits they may be used on. So I guess higher current applications such as power distribution and electric showers may benefit more than, say, lighting circuits, as circuits with more points or with a higher current carrying capacity may be more prone to suffering from an arcing issue. So there we have it, some questions answered on the AFDD, how it works and what it does. Although they're a bit new and unknown on the UK market at the time of recording, we'll probably soon see them becoming more commonplace. Those of you watching who are just starting out in your electrical careers may find yourselves all too familiar with such devices in the near future, whereas old dinosaurs like me will tune out with fond memories of simpler times, when such things didn't exist and consumer units were plastic and certificates were shorter. And not everything needed RCD protection, and you could buy 2 pints of beer for a £5 and still have enough change for the bus home, and they used to make music you could dance to.